February 1974, Malvern, Pennsylvania. The temperature inside the shop that winter sat somewhere in the low 40s, cold enough that the crew worked in jackets, warm enough that a man known across the sport for his short temper and shorter patience could still hold a wrench without his hands going numb. And in a converted garage behind a modest Pennsylvania engine shop, a 50-something former Cornell-trained mechanical engineer named Bill Jenkins, a man the entire sport simply called Grumpy, was quietly building a front suspension system that would fundamentally alter what every pro stock car in America looked like underneath for the next 5 decades. His name was already legend by 1974, 5 NHRA Pro Stock Championships, 61 national event wins across multiple categories, spanning superstock, modified production, and pro stock itself, a reputation as the single most influential engine builder drag racing had ever produced. But the car he was building that winter, a 1974 Chevrolet Vega that would become known as Grumpy's Toy X5, was not primarily about the engine at all. It was about something happening at the front of the car, a suspension geometry so different from anything else running in pro stock that when NHRA's technical inspectors first got a good look underneath it, several of them reportedly did not fully understand what they were looking at. Every other pro stock car in the country in 1974 ran some variation of a conventional double-A arm or straight axle front suspension, hardware directly descended from the production cars these vehicles were nominally based on. Hardware every engineer in the sport had spent a decade optimizing within a shared, well-understood design language, refined through countless incremental seasons of small, iterative adjustment rather than any fundamental rethinking of the underlying architecture itself. Jenkins showed up with a MacPherson Strut front end, a design pulled from European sedans and small economy cars, paired with rack and pinion steering, mounted in a purpose-built full-tube chassis that shared almost nothing structural with the Vega body panels wrapped around it. NHRA officials examined the car and found nothing that technically violated the rulebook. The suspension type was not prohibited. The chassis construction fell within the permitted safety envelope for the class. There was no part number, no material, no dimension that crossed a written line. And that is the part that should genuinely unsettle you. Because this was not a suspension built to be exotic for its own sake, it was built to solve a single specific problem that every pro stock team in the country was fighting and losing against. And Jenkins solved it using a piece of automotive engineering nobody else in the sport had thought to even consider borrowing from outside drag racing's own tradition. Within a few short years, that McPherson strut geometry and the weight transfer principle underneath it had become close to universal across the entire class, not because a rule forced anyone to copy it, but because every competing team eventually concluded there was simply no other way to keep up. Here is the part that should disturb you even more. The strut suspension itself was only the visible piece of a 5-part engineering approach Jenkins brought to that car, an approach built specifically around a single core insight about weight transfer and chassis dynamics that the rest of the sport had never formally understood, let alone deliberately engineered around. The pro stock car that quietly reshaped drag racing suspension design more permanently than any single car before or since, a car whose front-end geometry NHRA's own technical department spent years studying, trying to understand, and eventually could do nothing about except watch the rest of the sport copy it, one team at a time. Until the original design Jenkins had spent that cold Pennsylvania winter perfecting became simply how a pro stock car was built. I am going to show you the actual physics behind each decision. Not garage legend passed down secondhand for 50 years, the actual weight transfer mechanics, the actual suspension geometry, the actual engineering logic that let a man with a mechanical engineering degree from Cornell outthink an entire professional sport using principles borrowed from cars nobody in drag racing had ever taken seriously before. And I am going to make you a promise right now. You will understand exactly why a suspension system NHRA never once formally restricted became so dominant, so quickly, that officials privately worried for years about a single team's ability to keep finding advantages the rulebook had never anticipated needing to address. And the most uncomfortable part of that promise, nearly every pro stock car built after 1974, including cars fielded by Jenkins's own fiercest rivals, eventually adopted a version of the very suspension geometry that started in that cold Pennsylvania shop. Let's go back to the actual problem Jenkins was trying to solve, the one every pro stock team in the country understood existed but nobody had solved correctly. The weight transfer problem. Every team accepted as unsolvable. Every pro stock car launching off the starting line faces the same fundamental physics challenge. At the moment of launch, the engine's torque tries to rotate the entire car backward around its rear axle, a phenomenon every drag racer understands intuitively as weight transfer, the front end lifting and the rear end squatting as the car accelerates. This weight transfer is not simply a visual spectacle, it is the single most important factor determining how effectively a car's rear tires can convert engine power into forward acceleration, because more weight pressing down on the rear tires means more available traction, and more available traction means the driver can apply more power without the tires simply spinning uselessly. Every pro stock team in the sport by the early 1970s understood this principle in a general sense and worked to maximize it, primarily through rear suspension tuning, traction bars, and careful calculation of instant center geometry in the rear four-link or leaf spring setup. What almost nobody in the sport had seriously examined, Jenkins included at the outset, was the role the front suspension played in this same equation. The conventional wisdom, essentially universal across the class, treated the front suspension as a largely passive component during launch, its job simply to keep the front wheels pointed straight and support the car's weight while the real engineering work happened at the rear. Jenkins, drawing on his formal engineering education in a sport dominated by men who had learned their craft entirely through hands-on experience rather than classroom study, looked at that assumption and asked a question the rest of the field had never formally posed. If weight transfer during launch is fundamentally a question of how a car's mass redistributes itself under acceleration, then the front suspension's geometry, specifically how it allows the front of the car to rise and how quickly and how far it rises, is not a passive bystander in that process at all. It is an active variable that, engineered correctly, could be tuned to maximize exactly the same weight transfer effect that every team was already chasing through the rear suspension alone. This reframing is the foundation everything else in this story is built on. Jenkins was not looking at the front suspension as a system to be minimized or made as light and simple as possible, the way most competing teams approached it. He was looking at it as an underexploited lever for the exact same weight transfer advantage everyone in the sport was already fighting over at the rear axle, and that reframing alone put him a full step ahead of every rival team before a single wrench had even turned. The Strut. Geometry that let the front end rise on purpose. A conventional AA arm or straight axle front suspension, of the kind every other pro stock car in 1974 was running, has a specific, largely fixed relationship between wheel travel and chassis geometry, inherited directly from the production car it was derived from and constrained by the packaging requirements of a street-legal vehicle. Modifying that geometry to specifically encourage a controlled rapid front-end rise under acceleration while still maintaining safe, predictable handling characteristics was mechanically difficult within the AA arm architecture because so much of the geometry was locked in by the fundamental layout of the system itself. A McPherson strut suspension, by contrast, offered Jenkins something the conventional layouts could not: a comparatively simple, highly adjustable relationship between the strut's mounting angle, its effective pivot points, and the resulting wheel travel characteristics. Working with suspension specialist Roger Lamb, Jenkins engineered a strut geometry specifically calibrated to allow the front of the Vega to rise in a controlled, predictable, and dramatically more pronounced way during the initial moment of launch than any conventional pro-stock front suspension of the era was capable of producing. Here is the physics that made this matter so much. As the front of the car rises during launch, the car's center of gravity shifts rearward relative to the rear axle, which increases the normal force pressing the rear tires into the racing surface, which directly increases the maximum traction those tires can generate before breaking loose into wheel spin. A front suspension engineered to rise further and faster in a controlled way generates more of this beneficial weight transfer than a conventional suspension resisting that same movement through its own inherent geometry, simply by choosing a fundamentally different mechanical architecture and calibrating it specifically for that purpose. The rack and pinion steering paired with the strut suspension compounded this advantage further, reducing unsprung weight at the front of the car relative to the heavier, more complex steering linkages conventional pro-stock front ends carried, meaning less total mass had to be accelerated and controlled during that same critical launch window. Less unsprung weight at the front, combined with a geometry specifically engineered to maximize beneficial rearward weight transfer, produced a car that launched with a fundamentally different weight distribution profile than anything else in the class, all from a front suspension type that had never previously been considered relevant to pro-stock performance at all. We move now to the third piece of this combination, and this is where Jenkins's engineering background becomes most directly visible, because it required him to solve a structural problem the strut suspension itself created. The full-tube chassis that made the strut geometry survivable. A McPherson strut suspension mounts its primary load path through a single upper strut tower, concentrating suspension loads into a comparatively small area of the chassis structure, in contrast to a double A-arm system that spreads those same loads across multiple, more widely separated mounting points. On a production streetcar, this is a manageable engineering trade-off because streetcars are not subjected to the extreme, repeated shock loading of a drag racing launch. On a pro-stock car generating the weight transfer forces Jenkins was specifically engineering, the suspension to maximize. A strut tower mounted into a stout Vega unibody structure would have represented a serious structural liability, concentrating enormous repeated stress into a body shell never designed to handle it. Jenkins solved this by abandoning the Vega's stock unibody structure almost entirely, building a purpose-designed full-tube chassis, fabricated by SRD race cars to his own specifications, that extended completely through the firewall and provided dedicated, properly triangulated mounting points for the strut towers, points engineered from the ground up to handle exactly the load path a McPherson strut suspension generates, rather than points adapted, as every other team's chassis modifications were, from a structure never designed for that purpose in the first place. This is the piece of the combination that made the entire strategy actually survivable under real racing conditions, and it is also the piece that required resources and fabrication expertise most competing teams simply did not have immediate access to. A team could theoretically bolt strut-style front suspension components onto a conventional pro-stock chassis without fully re-engineering the surrounding structure, but doing so risked exactly the kind of structural failure that would have made the whole approach far more dangerous than beneficial. Jenkins's willingness to build an entirely new chassis architecture around the suspension concept, rather than retrofitting the concept onto an existing chassis philosophy, is precisely why his version of the idea worked reliably while early, less thorough attempts by other teams to copy pieces of it in isolation often did not. The fourth modification takes us away from the suspension itself and toward a decision that, on its surface, looks completely unrelated, but which directly reinforced everything the strut geometry was designed to accomplish: the weight reduction program. As long as the car retained street-legal appearance and safety equipment, Jenkins undertook an aggressive weight reduction program on Grumpy's toy X-Ive, using techniques including acid-dipping body panels to remove excess sheet metal thickness while retaining structural integrity, replacing steel components like the hood, bumpers, and rear hatch with fiberglass equivalents, and reinforcing critical areas with lightweight expandable foam injection rather than additional metal, all specifically calculated to strip weight from the front and body sections of the car while maintaining the class's mandated minimum weight through strategic ballast placement. Here is why this mattered so directly to the strut suspension strategy. A lighter front end, with less mass that needed to be lifted and controlled during the launch phase weight transfer, the strut geometry was engineered to produce, allowed that same weight transfer effect to happen more quickly and with less energy, lost simply moving unnecessary mass around. Every pound removed from the front of the car, and strategically relocated toward the rear through ballast placement permitted under the class's overall weight rules, directly amplified the benefit the strut suspension was already generating. This is the same underlying principle that governed the flywheel mass distribution and clutch calibration tricks that have appeared elsewhere in pro-stock and top fuel history. The recognition that where mass physically lives within a legal total weight matters as much as, or more than, the total weight figure itself. Competing teams inspecting Grumpy's toy Exine at the track noticed the lightweight body panels and understood in general terms that the car was built to be light up front. What took considerably longer for the rest of the sport to fully appreciate was that this weight reduction program was never simply about making the car lighter in an undifferentiated sense. It was a precisely targeted redistribution, engineered specifically to make the strut suspension's weight transfer geometry more effective than it would have been on a car that had reduced weight uniformly rather than strategically. We arrive now at the fifth and final piece of this combination, and this is the one that took the rest of the pro stock field the longest to fully understand, because it lived not in any single component, but in how Jenkins approached the entire car as one integrated system, rather than a collection of separately optimized parts. The integrated design philosophy that NHRA could never fully regulate. Against every individual piece of Grumpy's toy Exine, examined in isolation, was something NHRA's rulebook technically permitted. Strut-style front suspensions were not prohibited. Full-tube chassis construction fell within the class's structural safety requirements. Lightweight body panels, acid-dipped and reinforced with foam, met the letter of the class's weight and safety rules. Rack and pinion steering was not restricted equipment. NHRA's technical inspectors examining any single component of the car found nothing to point to, nothing that crossed a written line in the rulebook as it existed in 1974. What made the car genuinely difficult for the sanctioning body and for competing teams to respond to was that its actual competitive advantage did not live in any single one of those components. It lived in how precisely they had been engineered to work together. The strut geometry calibrated specifically around the weight transfer principle, the chassis built specifically to survive the loads that geometry generated, and the weight reduction program calibrated specifically to amplify the same effect the suspension geometry was already producing. A rival team could copy the lightweight body construction in isolation and gain some benefit, but replicating the full advantage required understanding and successfully executing the entire integrated system simultaneously, something that took the rest of the pro stock field years of iterative development to fully achieve, even after the basic concept was no longer any kind of secret at all. This is precisely the pattern that made Jenkins, and Grumpy's toy Exine specifically, a source of genuine, sustained institutional concern within NHRA during this period. The sanctioning body could not write a rule against an integrated design philosophy. It could only watch a single team, operating out of a modest Pennsylvania shop with a fraction of the resources of the larger factory-backed operations, repeatedly arrive at fundamental engineering insights that reshaped the entire competitive landscape of the class, faster than the rest of the sport could formally catch up, and faster than the rulebook itself could be reasonably expected to anticipate. There is a broader pattern worth naming here, one that extends well beyond this single car. Jenkins had already demonstrated years before Grumpy's toy Exine a consistent willingness to look at conventional pro-stock engineering assumptions and simply refuse to accept them as fixed. His earlier innovations, the kick-out oil pan designed to keep oil away from a spinning crankshaft under hard acceleration, the slick shift transmission technology adapted from earlier 4-speed racing to allow faster, more consistent gear changes, the cool-can-fuel cooling system that kept intake charge temperatures lower and more consistent than anything else in the class, all followed the identical underlying pattern that Grumpy's toy Exine would later demonstrate at a larger, more integrated scale. Identify an assumption the rest of the sport treated as fixed. Ask, with genuine engineering rigor rather than folk intuition alone, whether that assumption actually reflected a hard physical limit or simply an unexamined convention. Build a solution specifically targeting the gap between those two possibilities. By the time Jenkins arrived at the strut suspension and integrated weight transfer philosophy behind his 1974 Vega, he had already spent nearly a decade demonstrating, component by component, that this exact pattern of thinking reliably produced advantages the rest of the sport had not seen coming. Here is what I want you to sit with after this video ends. Bill Jenkins did not build a suspension system that violated a single word of the NHRA rulebook as it existed in 1974. He built a suspension system and an entire car around it based on a fundamental physics insight that the front suspension was an active, underexploited lever for exactly the same weight transfer advantage the rest of the sport was already fighting over at the rear axle that nobody else in the class had formally articulated, let alone engineered a complete, integrated solution around. The McPherson strut geometry, the purpose-built tube chassis engineered specifically to survive it, the strategically targeted weight reduction program, and the disciplined refusal to treat any of these components as separately optimizable pieces rather than parts of a single integrated system, together produced a car that permanently reshaped what a pro-stock front end looked like. Not because NHRA ever forced the rest of the sport to copy it, but because every competing team eventually concluded there was no other way to keep up. The McPherson strut front suspension, pioneered on Grumpy's toy Xide, had become close to standard equipment across the entire pro stock class, adopted by teams that had spent years initially dismissing it as an unnecessary complication borrowed from cars that had no business informing serious drag racing engineering. The dry sump oiling system Jenkins introduced on the same car followed a nearly identical path, dismissed at first, gradually adopted piecemeal, and eventually considered so fundamentally correct that building a competitive pro stock car without it became essentially unthinkable. Bill Jenkins did not need a single illegal part to permanently alter the trajectory of an entire professional racing discipline. He needed a mechanical engineering education most of his competitors did not have, a willingness to look outside drag racing's own design tradition for solutions nobody else in the sport had thought to import, and the discipline to engineer every piece of the resulting car as part of one coherent system, rather than a collection of individually clever tricks. And in racing, in life, the advantage that proves hardest to catch is rarely the one hiding behind a single hidden part. It is the one built from understanding a problem so completely, so far ahead of everyone else in the room that by the time the rest of the field finally catches up to the insight, the team that found it first has already moved 3 steps further down the road. Consider what genuinely separated Jenkins from nearly every other successful crew chief and engine builder operating in pro stock during this era. Most of the sport's leading figures had come up through the same informal, hands-on apprenticeship tradition that defined American drag racing throughout the 1950s and 1960s, learning engine building and chassis fabrication through direct experience, trial and error, and the passed-down wisdom of other racers. That path produced extraordinary practical intuition and an unmatched feel for what worked on the racetrack. What it did not typically produce was a formal grounding in the underlying engineering theory, the kind of systematic understanding of load paths, weight distribution mathematics, and structural mechanics that a university engineering program instills as a matter of course. Jenkins, with his Cornell training, could approach a problem like front-end weight transfer, not simply by testing variations empirically at the track until something felt faster, the way most of his competitors would have approached it, but by first reasoning through the underlying physics on paper, predicting where the gains should theoretically come from, and then building hardware specifically engineered to capture exactly that predicted advantage. This distinction matters enormously to understanding why Grumpy's Toy Xi represented such a durable, difficult-to-catch-up-to advantage rather than simply one more clever trick in a sport that had already seen plenty of them. A trick discovered through empirical trial and error, a lucky combination of parts that happens to work, can often be copied reasonably quickly once a rival team identifies which specific component or setting is responsible for the gain. An advantage built from a genuine, from first principles engineering insight, one where the person who found it actually understands the underlying physics well enough to explain exactly why it works, is far harder for competitors to fully replicate, because copying the visible hardware without understanding the theoretical reasoning behind it tends to produce an incomplete, less effective version of the same idea. This is precisely the pattern the rest of the pro stock field experienced when early attempts to copy pieces of Jenkins's strut suspension concept without the full integrated chassis and weight distribution philosophy underneath it, produced results that fell noticeably short of what Grumpy's Toy Xi itself was achieving. NHRA's own institutional response to this pattern, sustained across multiple seasons rather than a single controversial run or one dramatic technical inspection, reflected a genuinely difficult regulatory problem that the sanctioning body had not previously had to confront in quite this form. Earlier eras of drag racing rulemaking had generally responded to specific, identifiable pieces of hardware: an oversized engine, an illegal fuel additive, a component sourced outside what the rulebook permitted, each of which could be addressed through a targeted rule amendment naming the specific violation. Jenkins's advantage did not offer NHRA officials a single target to legislate against. Banning McPherson strut suspensions outright would have been a dramatic, almost certainly counterproductive step, since the design itself was demonstrably safe, effective, and, crucially, not actually prohibited by anything the existing rulebook said. The sanctioning body was left in the uncomfortable position of watching a single team's superior engineering understanding reshape the competitive landscape of an entire class, with no clean regulatory lever available to slow it down, without also punishing every other team that might eventually want to adopt the same, entirely legal, engineering approach. This is why period accounts from competing crew chiefs and even some NHRA technical staff describe a genuine, sustained institutional wariness specifically around Jenkins's shop during the mid-1970s, a sense that the sports rulebook, written by people without Jenkins's specific engineering background, was structurally unequipped to anticipate the next fundamental insight that might emerge from that small Pennsylvania operation. That wariness was not really about any single suspicion of rule-breaking, because nothing about Grumpy's Toy XI's front suspension ever crossed into territory that required a rules violation to explain it. It was a more fundamental concern about competitive balance itself, the recognition that a sport built around a shared rulebook depends on that rulebook being written by people who can actually anticipate the kinds of engineering insight a formally trained mechanical engineer, operating without the constraints of a large factory bureaucracy, might arrive at next. The McPherson strut front suspension's eventual near-universal adoption across pro stock tells its own story about how thoroughly this specific insight reshaped the sports engineering consensus. Teams that had spent years publicly dismissing the strut suspension as an unnecessary, overcomplicated solution imported from cars that had nothing to teach serious American drag racing engineering quietly began adopting versions of it themselves once the performance gap it created became too large to ignore through any other means. That reversal, watching rivals abandon years of stated skepticism the moment their own competitiveness depended on it, represents its own kind of vindication for an insight that had originally been treated, by nearly the entire rest of the professional drag racing establishment, as eccentric rather than correct. Bill Jenkins passed away in 2012, remembered across the sport not primarily for any single race win or championship, though he collected plenty of both, but specifically for the sustained pattern of fundamental engineering innovation that Grumpy's Toy XI represents at its clearest. Dry sump oiling systems, strut-style front suspensions, kick-out oil pans, slick shift transmission technology. Nearly every one of these innovations followed the same basic trajectory, dismissed initially by a sport more comfortable with empirical trial and error than first principles engineering theory, gradually proven correct through sustained competitive results, and eventually adopted so universally across the class that later generations of pro-stock racers grew up assuming this was simply how the cars had always been built, with little awareness that a formally trained mechanical engineer working out of a modest Pennsylvania shop had been the one to prove it correct in the first place. One cold winter afternoon in 1974, using nothing but a piece of automotive engineering nobody else in drag racing had thought seriously worth borrowing.